He must be around. He's okay.
Okay, hello. I'm sorry, I was getting ready.
Good.
Okay, thank you for inviting me to be here. It's a great pleasure, and it's my second time in Turkey after Antalya, and that conference was also fantastic. So today I want to tell you a little bit about topological quantum computing as being a very far goal, and how we are trying to build up toward that goal, and how it actually passes through the old quantum Hall physics that we all know as one of the most robust topological systems. So this is the work of my group, in particular Mehdi Hatefipour, who actually pioneered a lot of this work in my lab. Okay, I'll get used to this. Perfect. So, okay, that wasn't me. It is going down. One time. Okay, I will just keep. Okay, press harder. Okay. So very briefly, I want to kind of motivate quantum computing again and why we think the way we think. And yesterday there were beautiful talks by Irfan and Roland about kind of the topological aspects and superconducting aspects. But I think this is a very generic line of thought that if this is the merit of quantum computing, how fast we can compute, the power of computing, and this is the number of years, what we should appreciate is that when technology changes from vacuum tube to transistors, we definitely have more power in terms of computing. Then we went to integrated circuits. And now there is this next generation thing that will come, and then that could be quantum computing or something else. But I did not press anything. Okay. So what would that be? And again, I think based on Moore's law and everything getting smaller, the quantum technology is probably the most relevant technology to look at, especially in solid state in my mind. A very brief overview that I would like to connect to quantum Hall later on and discuss why I think it's a very interesting system is that the qubits are basically a two-level quantum system that we describe by Schrödinger equation. This is a 101 type description. But what I like to emphasize is that this two-level system is separated by an energy, but those energy levels could be also broadened. And that is usually related to disorder or dissipation. So all the qubits that we have talked about so far, these are, I would call them, again, first generation, in the sense that you will find the two-level system in your materials that you like, diamond vacancies, ion traps, and these are perfect quantum systems. The problem is that there is no intrinsic protection from relaxation or decoherence. We basically found the first two-level system we could, and we are trying to kind of operate it as a qubit, which is great, and we have made great progress in the last 10 years. But to go now to do the harder thing, the stuff that Irfan was talking about yesterday, now these things are basically opaque. Anything can harm them, the cosmic ray, everything. And because the information is basically placed in such a small and simple system. How can we look at this problem in another way? When things are very small, they are prone to error. A very poor man's version of showing this is that if I have a length scale problem, and this is atomic scale, and this is macro, and I know that the small things I can have quantum theory, I can ask an interesting question. I can say, what is the longest length scale that I'm completely dominated by quantum effect? And instead of going Moore's law that was classically pushing me this way, now I'm asking a new question. I'm saying like, can I be at millimeter and have quantum theory completely dominant? If that's true, can I have a two-level system at that length scale? And at that length scale, my resolution of like 10, 20 nanometer of avionics or nanofabrication or whatever that we use is very, very sophisticated for that length scale. But if I want to control like a 2 angstrom NV center, then I'm kind of out of tool unless there are some accidental stuff. And in reality, there are things that actually work in millimeter scale. Like quantum Hall effect, you can make a sample that are like 5 millimeter and you're still going to get a quantized value. You can make a superconducting cavity that is also a few millimeter and it still works. And going back to my very simple qubit picture, you basically need to beat these two things. The temperature has to be small enough that you can resolve the two-level system. Your dissipation should also be much smaller than the energy scale. In superconductivity, that is easy. This is 0. And you basically cool down to below TC. If your energy level is good, you're done. Quantum Hall is kind of the same thing. If the material is clean enough, like gallium arsenide, 30 million mobility, basically all of this checks out. And if you look at it in this perspective, there actually has been a handful of, I would say, Nobel Prizes that went to this direction of how we can actually get the quantum effect into larger length scales, whether by accident or was by design. So great. So we have things that do not have any intrinsic protection. We have things that now the quantum is taking them to the longer scale. So what can we do? Can we make a second generation qubit that basically are in this new regime? And that's indeed, I would say, the last 3 years or 4 years of qubit research is going toward that direction with a name called protected qubits. These are the qubits that you basically make the Hilbert dimension like redundant, so when the error comes in, it doesn't like scramble your information. The most famous one is cat code that came out from Yale by Mazjami Rahimi and Michel Devoret and Rob Shorkoff. And this is one of the best, I would say, qubits that we have these days. There are like at least 10 of these different variations. But then there is also this topological version. And these topological versions come in a variety. I guess the most famous one is Majorana fermion that we discussed. But that's not the only one. And I will show you in a second that that's why that is the case. But when I say topological, I basically mean that I have a degenerate manifold at the zero energy. And if the operation is that I get these two particles and basically bring them down, and somehow a truck is passing by or I have some noise in my system, and this line becomes wiggly, topologically I've done the same thing here as I was supposed to do it there. Or if I am supposed to braid this thing, this would be sort of the equivalent picture of that. And because of that, this is much more forgiving for quantum computing compared to actual qubits. So what should I do? So the work originally in quantum Hall effect in terms of non-Abelian physics and Pfaffian started with Reed Green, and then by Adi Stern, by Kitaev. The best translation, at least for an experimentalist, is this paper by Chet and Nayak in 2008 that basically they put everything in sort of one concept of how non-Abelian anyons and topological quantum computings are related. And going through this paper, you can also create these kind of mountains of milestones in very long scales, time scales, that basically starts with, we first need to find a system that hosts non-Abelian physics. That is Majorana in a nanowire, that's something on quantum Hall, whatever that is, we need to figure out those systems and engineer them. Then we have to control the Majorana. We have to be able to move things and braid things. Majorana will only give you two gates out of the 4 gates you need for universal quantum computing. Parafermion will give you 3 protected gates, and Fibonacci will give you all protected gates. So even getting Majorana, although it's fantastic, it's not the end of the game. This thing will continue. But today, as Irfan showed on his last slide on the Alps, we are talking about just how we're going to design our experiment to get to this kind of physics. So what are anyons? I keep saying anyons. If you haven't heard about it, this is actually nothing very particular. If I have a many-body system and I exchange 2 particles, I and j, together, you can define it as an operator. If I pick up a sign, like a minus sign, that's a fermion. That, it's just Ashcroft-Mermin type things, right? If the sign doesn't change, that means all the particles are identical. I have a boson. So this is very standard in condensed matter. Anyon is basically systems that will pick up this operator is a phase. So for example, if theta is 0, this operator becomes 1. If it's pi, you will get a -1. But it could be anything. It could be pi over 3, right? So all of these, these are all abelians. But because they can get any phase, we call them anyons, basically any phase particle. So that's great, but this is proven that it's not very useful for quantum computing. What you want is an anyon that also has a non-Abelian behavior, a statistic. So what does that mean? Good. So this was the standard anyon. The non-Abelian version is that you can no longer have a phase change when you exchange 2 particles. Basically, it means that unitary is not just a diagonal e to the power of I theta. It's basically a matrix, and that matrix is very unique to the physics we're discussing. If it's Majorana, it's going to be something. If it's 2 pairs of Majorana, it's going to be different than 5 pairs of Majorana. So in case of 2 pairs of Majorana, if you basically define your qubit state by basically the digits that are the occupation number of fermionic mode, 0011, the standard qubit system, and you calculate the unitaries in this system. Basically, U1, 2 means I change Majorana 1 and 2. These belong to the same chain. And then there is another one that basically is 3 and 4. So 1 and 2, you can easily see that basically is diagonal and is a phase. So that's not going to give you anything interesting. But if you do connect the chains, if you try to break the 2 and 3, now you can see you have off-diagonal elements. That what it's going to do is that if you just apply it to your ground state, 0, 0, it's going to take you to a superposition. That's exactly what non-Abelian physics will give us at our manifold. That's fantastic, but how can we actually get one? So there are many, many proposals out there. It actually, a lot of it started with 5-half physics in quantum Hall effect. You know, the atomic chain we heard about yesterday, nanowires, this is my research, mercury telluride. But today I want to talk about this particular proposal. This proposal is trying to basically, I guess, discount the 5-half requirements. The 5-half physics only shows in gallium arsenide under really low temperature and highest mobility, and the gap is almost only 300 millikelvin. But if we somehow move that to an integer quantum Hall effect, then we can actually use a lot more bandwidths in terms of controlling it and the stability. The price we pay is now we need a superconductor to actually interact with quantum Hall effect. So there are a series of proposals that actually came maybe too early before the experiments could actually try them. But then later refinement on these proposals basically identified that this very pictorial picture has to be different in a way that you put a superconductor in the middle of this Hall bar. This is n equal to 1 with one chirality. There is this chirality, which is the same, but now you have two opposite edges that are going to basically be coupled through a superconductor. And that's exactly what will give you a Majorana physics. How do you do parafermion? In the other proposals I showed you, like the atomic chain, there is no way you can do parafermion. Here, if you change this n equal to 1 to 1/3, you get a fractionalized Majorana, and that is basically parafermion. So that's quite straightforward here. Okay, so I need a superconductor talking to my quantum Hall effect. And what I need as a precursor is to see Andreev states, right? Basically, I want Andreev reflection in magnetic field. To just remind you what is an Andreev reflection, at zero field, you get an electron hitting on a superconductor, a hole is going to come out, and a Cooper is created and goes inside the superconductor, right? In a very naive semi-classical picture, when magnetic field is no longer 0, this is the scenario. The electrons in an edge state mode will come to the superconductor. They become a hole. So they now have to have another, basically, circle. They go back to electron, and then they kind of hop and back and forth, right? Quantum mechanically, I have to write that as a superposition. I can't write it as a, basically, a hopping. So what do I need? I need to interface superconductor with my quantum Hall. We have done a lot of epitaxial work of how to put superconductors on indium arsenide with great quality. And we can show that we can get transparencies that are exactly 1. Okay. So this was supposed to be a video, but basically we have 2 decks at the surface. If you want your superconductor to talk to your 2 deck, the 2 deck has to be at the surface. The mobilities are around 40,000. You can see a couple of quantum Hall states. And we use niobium nitride here on top of the aluminum. And that critical field is about 28 Tesla. So we can actually cover the whole range of quantum Hall effect here. So this is the device. It's basically a Hall bar. Indium arsenide is green. This is niobium ti. There is a gate voltage that covers everything. So we can change the density here. So what do I need? What do I expect? In a very simple quantum Hall system, when all the contacts are great, you basically measure 0 for your RXX or longitudinal, and then you measure the Hall data for your Hall measurement, basically when you measure across. When I change one of these contacts with a superconductor, now I have to actually include the effect of Andreev reflection. So this is kind of a modification on Buttiker formula that basically my reflection plus T that was 1 for normal contacts, now I have a contribution from the Andreev states. So basically the bottom line becomes that for Andreev states, I didn't touch it, okay, is that you basically, the Andreev parameter enters your Hall data and your longitudinal resistance. And what you would expect, I will just cut for time, is that in an ideal case, when Andreev reflection is perfect, and instead of 0, you will measure minus h divided by 2 squared. And in the case of, again, perfect Andreev reflection, you measure half of the Hall data. So Hall data goes from this value to half of it, and then the RxS goes from 0 to minus that half. And if it's non-ideal, you get kind of sit somewhere in the middle, right? You basically will be between 1 and this basically factor of 2. So we make these devices. We actually put a great care in terms of getting these interfaces right. So this is the interface, almost like the optical image I showed you. We measure RxX, 2 normal contacts. Current goes from one side all the way to the other. This is magnetic field as a function of the top gate voltage. And you see the integer quantum Hall effect is very clear. The resistance goes to 0. Everything is normal. Now what I would do, I would actually measure across this interface where there is Andreev reflection. So now if you look at the same graph, now basically I'm just plotting this downstream. This downstream is between 5 and 4 prime. And now you see these strong blue color regions, exactly where the quantum Hall is supposed to be. These are now at minus almost 1 kilo ohm. So now we see a very negative resistance when we look at across the interface. So that's promising, at least within the Buttiker formula. That's exactly what we expect. If you want to see it better, I can get a line cut at 11 Tesla. And this is RxX on basically gray line, as you see. And then blue is across the interface. And as you see, blue, whenever it's supposed to show a quantum Hall effect, it actually goes to a negative number. Right? What about Hall data? I also said Hall data has to drop. So Hall data, the black is again the standard Hall data in the middle of the sample. The blue is across the interface. And as you see, whenever we get to a quantum Hall effect, the Hall data basically drops below, right? And that difference is exactly that difference. If you add them up, you recover the Hall data. So what if I actually measure farther? Like I measured from 4 to 3 and then 4 to 2. If there is no dissipation across the quantum Hall, basically the resistance shouldn't matter. And as you see, basically blue and red are such experiment. Red is as 4 times L. The blue is 2L, and as you see, the quantization value somehow doesn't change, but then the graph's obviously very different above that value, right? So once you are basically getting to the Andreev reflection, that number is fixed, determined by that interface, not the length and the contact or the normal contact variation. So if you believe on those data, basically the formula of this Hall data, I basically said is relevant to the Andreev reflection. I can basically plot these lines, and then basically as a function of different field, deduce an Andreev coefficient. The Andreev coefficient we find is basically 20%, which is quite high for a system that is basically operating at 10 Tesla. If you compare to graphene data, basically they get 1% almost. And here the advantage is this epitaxial contact that we can make to our indium arsenide. We also got worried that maybe there was something wrong, maybe this was an accident, whatever. We made like 8 or 9 samples, and in every single one that the interface is good, we actually observe a negative resistance. And the variation comes from the fact that how perfect is in the interface. When the interface is clean, you see the highest negative number. When the interface is not clean, deliberately you don't clean the interface and let it oxidize in air and you put it in the chamber, now you see that there is this number drops to 8 ohm instead of minus 800 ohm. So it's a direct interface problem. You compare it to graphene data. This is our data. This is the data by, I believe, Duke. And then you see that basically minus 100 ohm versus minus 800. These are also minus 20 ohm or so. So basically, I think there is a direction that a lot of people are kind of following in quantum Hall effect by adding superconductors, niobium nitride, molybdenum rhenium, and niobium trinitride that we did. And I think the best Andreev reflection has been achieved by us. So why all the qubit business? The topological gap at the end of the day is going to be very important. So what we did actually in one of these experiments, we basically put a QPC right across that interface. So half of the QPC is covered in niobium ti, half of it is covered in 2-dec. So by this operation, now I can look at the induced gap at the quantum Hall effect in niobium trinitride. And this is the number, 700 microvolt when you are at 6 Tesla at the quantum Hall effect. So this 700 microvolt, you have to compare it with these Majorana gaps from Microsoft and other people that are only on the order of 20 microvolt. So if we can actually create Majoranas in the system, this would be a great host because the topological gap is already strong. So we see another experiment you can do here, which I'm going to briefly mention, is that if you have a just coming up this, some of them can go through the QPC. With QPC, you can actually allow the select number of modes that go inside or get reflected back. It's basically your tunable mirror. And if they go inside and get reflected back as a whole, you kind of see this quasi-hole that comes out that can actually now interfere with the electronic system. And the result is an oscillation around the quantum Hall states when you go to 0. So we are actually studying that. Let me just skip this and get to the summary. So I think we have managed to basically make this niobium tinitride indium arsenide with really high quality interface. We observe this negative resistance that actually matches the presence of Andreev reflection in these systems. And we also have found these Andreev reflections can get up to about 15 to 20%, which I would say is the record number for these systems. So now we are trying to actually go to the next level, which basically is now coupling different quantum Hall states together. Thank you so much.
Okay. Thank you very much. Perfect timing. And okay, please, questions?
I have a question. You mentioned the non-Abelian anions, like, for example, the 5 halves states. Do you know if the non-Abelian character has been explicitly, experimentally measured?
I don't think so. I don't think a non-Abelian character has been measured in any system.
Right.
Even if on the Majoranas, if you cannot fuse them to get the algebraic relationship, or you break them, which is harder than fusion, there is no way to say that these are non-Abelian or not, right? So basically, if you do if you fuse 2 of them, whether you get empty or you get I, right, the psi daggers. So that experiment has not been done on anything. Even on nanowires, it hasn't been done, because you need 2 pairs or 2 anions deterministically to fuse them, right?
Correct. So I just wanted to point out that even for the simpler series, it's not even clear now if the anions are abelian or non-abelian. There are 2 competing series. One is Ven's Chern-Simons series.
Yeah.
One is a theory which is based on W algebras, which gives non-Abelian character already at 2/5.
I see.
So maybe one can use even simpler.
12/5, I see. Yeah, yeah.
But
No,
I think nobody has established if
right.
measured.
No, indeed, indeed. I think in quantum Hall, especially on 5/2 and 12/5, the gaps are so small that even measuring a gap is not right. Making a mesoscopic thing, which is an interferometer, that's even harder. And on gallium arsenide is almost impossible. So the hope is that with this superconductivity, you mimic that physics in a regime that you have more control. You test it. It could be a failure. It could be a positive signal. So we'll see.
More questions? Then maybe I have a completely different question. Since you seem to use niobium nitrate there,
Niobium tinitride.
yeah, you can expect that when you make a qubit, at long last, it will be very well coherence protected. Is that correct?
Right.
Because
yes.
you have huge kinetic inductance because of this. So what's your, if you have some estimate for?
Right, right. I mean, if you find out, going back to the first question, if I can show this is non-Abelian, I think that's already, a great achievement, right? Yep. To make a qubit is just going to get 10 times harder, right? And the reason is that on top of everything else, the Majoranas are not infinitely long, right? The coherence lengths of Majoranas are actually disrupted by the quasi-particle poisoning. Because once basically we lose the parity in our manifold, the topological protection is gone, at least the way that we have defined it. And that basically is a random particle that comes to the gap. Niobium tinitride is one of the worst because it's a granule superconductor. If you want to get the best quasi-particle protection, you go to aluminum. But then aluminum doesn't survive the field. So I would say this is a toy experiment for non-Abelian physics, if it's there. And if you want to make a qubit, you basically have to drive this back to the 0 field. And again, I guess there was a talk by some quantum Hall anomalous physics or some material that 0 field can work with things. And then you can bring aluminum back and then go from there. But those materials are not as ready, I would say. And then here you have a very, very established quantum Hall physics, which is understandable. So it makes the interpretation a little bit easier. But once you work at 10 Tesla, I mean, there is almost no hope for making a qubit either way.
Thank you.
Okay.
Well, more questions? Well, if not, then
Thank
we
you so
have
much.
to thank the speaker.
Thank you so
One more
much.
time.
Thanks.